So as a diagram, I drew the disk, the flat disk, with the center at the origin of the xy plane. And I drew a small area of charge that I designated Q, which is a distance little r from the center. And the radius of the disk is big R. So to find the magnetic field of a single point charge Q, we use this equation. And because r hat is just a direction, it can go to 1 and just cancels out. Also, because it's the cross product, you have to multiply the velocity by the sine of the angle that the radius is at. And because the velocity is an angular velocity, it's always going to be perpendicular to the radius. So that just acts as a 90-degree angle. And since sine of 90 is 1, it can just be simplified to 1. Which leaves us with this equation here. And we want to find the magnetic field in relation to the density of charge per area, which is related by eta times the area. Then you can substitute Q equals eta A for the small amount of charge per area and substitute it for dq. Because this is angular velocity, we know that velocity is equal to omega r. And then once that's simplified, we get this. We also know that the area of a circle or disk is pi r squared. And to find the area of a small section of that disk, you just have to take the derivative of pi r squared, which leaves you with 2 pi r dr, which can be substituted into the equation and simplified. Leave us with this. And to find the amount of charge over the total disk, we have to integrate that equation from 0 to r, because the radius of the disk starts at the origin, which would be 0, and goes to length r all the way around the circle. Because this whole section of the equation is just a constant, we can pull it out in front of the integral and just integrate dr, which leaves us with capital R, which would be the radius. And we know that we need to factor out the eta and replace it with Q over A. And we know that eta can be, and we know that the area can also be substituted as pi r squared. So all of that simplified down is just equal to that.